condition. Today we shall study about ray optics and optical instrument in optics, electromagnetic radiation belonging to this region of a spectrum, wavelength of about 400 nanometer to 750 nanometer is called light. There are two things that we can intuitively mention about light from common experience. First, that it travels with enormous speed, and second, that it travels in a straight line. It took some time for people to realize that the speed of light is finite and measurable. Its present value in vacuum is C barabar 3 × 10⁸ meter per second. The wavelength of light is very small compared to the size of ordinary objects. A light wave can be considered to travel from one point to another along a straight line joining them. The path is called a ray of light, and a bundle of such rays constitute a beam of light. We study the phenomena of reflection and dispersion of light using the ray picture of light, using the basic laws of reflection and diffraction. We shall study the image formation by plane and spherical reflecting and diffracting surface. We then go on to describe the construction and working of some important optical instruments, including the human eye. Reflection of light by spherical mirrors. Laws of reflection. There are two laws of reflections. The angle of reflection, it means the angle between reflected ray and the normal to the reflecting surface or the mirror equals the angle of incidence, angle between incident ray and the normal. Second, the incident ray, reflected ray and the normal to the reflecting surface at the point of incidence is in the same plane. This is valid for both plane or curved pole. The geometrical center of a spherical mirror is called its pole. Optical center. The geometric center of a spherical lens is called optical center. Principal axis. The line joining the pole and the center of curvature of the spherical mirror is known as principal axis. In the case of a spherical lens, the principal axis is the line joining the optical center with its principal focus. Sign convention. The distance measured in the ray, in the direction of the ray, is taken as positive, and against the direction of ray is taken as negative, as shown in the figure. Now, the figure 1. For focal length of the spherical mirror, as shown in the figure, all reflected light rays are meeting at a point F, that is focal point of the mirror. The figure 1 shows the happening when a parallel beam of light is incident on a concave mirror and convex mirror B. We assume that the rays are paraxial. They are incident at point close to the pole P of the mirror and make small angles with the parallel axis. The reflected rays converge at a point F on the principal axis of a concave mirror. For a convex mirror, the reflected rays appear to diverge from a point F on its principal axis. The point F is called the principal focus of the mirror. If the parallel paraxial beam of light were incident, making some angle with the principal axis, the reflected rays would converge or appear to diverge from a point in a plane through F normal to the principal axis. This is called the focal plane of the mirror. The distance between the focus F and the pole P of the mirror is called the focal length of the mirror, denoted by F. We now know that F barabar R by 2, where R is the radius of curvature of the mirror. Let's see with the center of curvature of the mirror consider a ray parallel to the principal axis striking the mirror at M. Then CM will be perpendicular to the mirror at M. Let theta be the angle of incidence and MD be the perpendicular from M on the principal axis. Then principal axis, then CM will be perpendicular to the mirror at M. Let theta be the angle of incidence and MD be the perpendicular from M on the principal axis. Then कोण MCP बराबर theta, कोण MP बराबर 2 theta. Now tan theta बराबर MD बटा CD and tan theta बराबर MD बटा FD. For a small angle theta, which is true for paraxial rays, tan theta बराबर theta, so tan theta बराबर 2 theta. Therefore MD बटा FD बराबर 2 MD by CD और FD बराबर CD by 2. Now for a small angle theta, the point D is very close to P. So FD बराबर F, CD बराबर R and F बराबर R by 2. Now mirror equation is shown for a concave mirror. In the figure 1, ray diagram is shown. We consider a concave mirror MP and the object is placed at principal axis AB. The real image is formed at A dash by intersection of reflected rays at M and P. The focal length is F, object distance is U, image distance is V. The ray diagram is then shown above by considering 3 rays. Now we take the 2 right angle triangle A dash B dash F and MPF. For paraxial rays, MP can be considered to be a straight line perpendicular to CP. So B dash A dash बटा PM बराबर B dash F बटा FB और B dash A dash बटा BA बराबर B dash F बटा FP. Since कोण APB बराबर angle A dash PB dash, the right angle triangle A dash B dash P and ABP are also similar. So B dash A dash बटा BA बराबर B dash P बटा BP. Comparing with both, we get B dash F बटा FP बराबर B dash F minus FP बटा FP बराबर B dash P बटा P. By applying sign convention, B dash P बराबर minus V, B dash P बराबर minus V, FP बराबर minus है, BP बराबर minus U. By sign convention, इसलिए minus V plus F बटा minus F बराबर minus V बटा minus U और V minus F बटा F बराबर V by U और V बटा F बराबर 1 plus V by U. Dividing by V, we get 1 by F barabar 1 by V plus 1 by U. This is called the mirror equation. Now the linear magnification is the ratio of height of image bata height of object is equal to H dash bata H, where H dash is the height of image and H is the height of object. Barabar minus V bata minus U barabar minus H dash bata H barabar V by U, because the image is inverted and real.